Good morning, guys and girls. Hope everybody's doing well. Today, what I wanted to do for you guys is get us started into the next bit of material, which is all about mixtures. As you can see, a couple housekeeping things just before we get going. Exams have all been sent my way. I am chipping away at those. I'm hoping I can get through probably 10 to 15 a day, um, on top of the ones that I already got graded over the weekend, which was probably another 15 or so. So hopefully I can have those posted by Wednesday or Thursday for you guys there in the grade book so you can see how the exams went for you. In the meantime, you'll get a parent square message that has this PowerPoint attached and tonight's homework, which is page 400, numbers 1 through 5, which will also be attached. So at the beginning of each chapter, I always try to revisit what we talked about from the beginning of the year and what it was that we hoped to accomplish going through Chem throughout the course of the year. Right? And one of those things is mixtures. So to kind of put that into perspective for you, all right, it falls into what we called classes of matter, which were one of the two major categories that I wanted to do, right? We wanted to talk classes of matter and we wanted to talk phases of matter, right? And we pretty much have rounded out most of what we need for phases of matter. You guys just sent me a test on solids and liquids, and we've covered gases. So we now know a lot about solids, liquids, and gases. Classes of matter, we know quite a bit as well. Right? We learned about elements earlier on. We learned about compounds earlier on. And the third class of matter is mixtures, which we do not know a ton about. So that's where we're going in this chapter. Right? So refresher on elements, right? Remember, elements are simply periodic table things. We've got metals, things to the left of the staircase, non-metals, things to the right of the staircase, and metalloids, the things that touch the staircase. And each of those things has their own properties. They have their own nucleus, right? But it's one individual thing all by itself. When we start to combine those together, we get compounds. And compounds come in a couple versions, right? We get ionic compounds. And remember, an ionic compound is what we get if we bind a metal with a non-metal. Or we get covalent compounds, which is a non-metal with a non-metal. But the big thing is when those substances come together, they each give up their properties and create a new substance with its own properties. I take sodium metal, which is an element, and it's soft, right? It's not edible, things like that. I put it with chlorine, which is an element. Chlorine is a gas. It's greenish. It's poisonous, right? But when they come together to form the ionic compound, sodium chloride, it's table salt. That poisonous characteristic is gone. The lack of edibleness and the softness of the sodium metal is gone. Sodium chloride gets its own characteristics. So when elements come together to form compounds, they forfeit their properties. So mixtures then are kind of the other side of that coin. Mixtures do exactly what they say. They mix these other two classes of matter together, right? So we can get a couple different varieties. We could get an element with an element, creating a mixture. We can get an element with a compound, creating a mixture. We could get compounds with compounds, creating mixture. But the big difference is that each of them keeps their properties, right? When I show you a mixture of air, which has oxygen, nitrogen, hydrogen, helium, a bunch of elements in it, they don't forfeit their characteristics when they become air. They stay that way, right? We use the oxygen from the air to breathe. So they haven't given up their individual properties. And that's the biggest difference between them. All right. Compounds, they give up their properties. Mixtures, they keep their properties. So we're going to focus in on mixtures, right? These different combinations and how they keep their properties and what the outcomes tend to be. All right, so if we look at that, we're going to talk about two fundamental types of mixtures and then three more specifically. First, you get homogeneous mixtures, and that's not a new term. We've talked about homogeneous before. We always say it is uniform. It looks like one thing. So if you create a mixture which has multiple things in it, but it still visually looks like one thing, we have a homogeneous mixture. For that reason, all elements and compounds are homogeneous because they are only one thing, right? Hydrogen is only one thing. It has to look like one thing. Right? Carbon is only one thing. It has to look like one thing. Carbon dioxide is two elements, but remember, they gave up their properties to form that new thing, that new one thing. So all pure compounds are homogeneous. Heterogeneous things we see the pieces of, and this comes from mixtures. We can see the different pieces in certain mixtures. Some mixtures we can't see the pieces of. All right, so we get three different types of mixtures. We get solutions, we get suspensions, and we get colloids. All right, and today I'd like to talk to you about each of those things and then take it a step further and look at substances and decide which of those are they going to be. All right, so the first one up will be solutions. What are your characteristics of solutions? All right, first characteristic of a solution, it's homogeneous. It looks like one thing. Second characteristic, it has very tiny particles. Right, so the particles are very, very little. So nanometers is how we're measuring the particle size. Remember, that's times 10 to the negative ninth. So we're talking really tiny particles. And because the particles are so tiny, some things happen with solutions. One of which is that I cannot filter a solution. Right, so if I have two different substances and both of their particles are very small, when I take that substance and pour it into a funnel that has filter paper in it, all of it goes through, right? The whole thing goes through because all the particles are tiny enough that they fit in the pores of the filter paper. So even if there were three different substances in here and it's a solution, all three end up down here. So you can't separate a solution by filtering. Another characteristic of solutions, they do not separate while standing. Separating while standing means it will layer when we just let it sit. So if I let these test tubes sit here indefinitely, you won't see them pull apart into a blue layer and a red layer or a green layer and a clear layer. They are uniform throughout. They don't separate while standing. That is something that solutions I'd have about them. So they're homogeneous, very tiny particles, they can't be filtered, and they don't separate while standing. What about our colloids? Colloids are heterogeneous. We should be able to see the pieces. The reason we can see the difference in pieces is they have medium particle size. So the pieces get a little bit bigger so we can start to differentiate between the two pieces. We're into the 1 to 1,000 nanometers in size. Like a solution, they won't separate while standing. Their particles are big enough that we can see them, but not so big that they'll pull apart. So if you look at these guys, they aren't splitting into layers. They still look like one thing, not layering out, but we can see that there's more than one thing in there, right? Because it's kind of cloudy, it's kind of foggy, right? The last thing then is because the particles are still pretty small, they cannot be filtered either. You take a colloid, you pour it through here, it will all go through the filter paper as well. And so your colloids are heterogeneous. They have medium particle size. They do not separate while standing, and they cannot be filtered. Last but not least, you have your suspensions. Suspensions are totally different than the others. Suspensions are heterogeneous. they have really large particle size. Because the particles are so large, they will separate while standing. All right. Think of marbles in water. If I'm shaking it, it looks like this. But the moment I stop shaking that beaker with marbles in it, the marbles will fall to the bottom and the liquid will sit on top of it. Right? It separates while it sits, while it stands, right? A standing order is one that's in place all the time. So if it's sitting there, right, it's standing. Right? And because the particles are so large in size for a suspension, it can be filtered. If I took this beaker and I dumped it into my filter, the marbles will get stuck in the filter and the liquid, whatever it may be, will go through, right, the filter underneath. And they give those names. The bottom part is called the filtrate, right? And sometimes the thing in the filter is called the precipitate, which we've talked about. All right, but that would be a suspension, right? Heterogeneous, big particles, it separates while standing, and it can be filtered. So when we're looking at substances, right, how can we tell the difference, right, between these things? All right, well, the first thing you want to do is decide if it's a suspension or not, because it's the easiest to spot. All right, so we check to see if it's a suspension first. How do we do that? Well, if you look back on those previous slides, you'll see suspensions are the only ones that separate while standing or can be filtered. So you ask yourself, is the substance I'm asked about something that'll separate all by itself? Or if I pour it into a filter, will some of it get stuck in the filter and some of it go through? If the answer to that question is yes, it can be filtered or it separates, you know it's a suspension. If the answer to that question is no, you know it's not a suspension, which means the other two are still fair game. It's a solution or it's a colloid, because solutions would all go through the filter, so would colloids. Solutions don't separate while standing, neither do colloids. All right, so how do we tell the difference then between your solutions and your colloids? All right, there is this thing called the Tyndall Effect. Right, and one of the big differences between solutions and colloids is what they do with light. In a solution, all the particles are so similar in size and tiny that when I shine light on it, light basically interacts with them all in one way, so the light looks one way. But in a colloid, you've got some smaller pieces and some medium-sized pieces, and those pieces can be different, which means when I hit them with a light beam, they'll respond differently to the light beam. And that's known as the Tyndall effect, how it, fancy word, disperses light. All right, so they ask you, does it scatter light? If it scatters light, it is a colloid. If it does not scatter light, it is a solution. So if I shine a flashlight or a laser beam or something like that through two beakers, and one's a solution and one's a colloid, in the solution, the particles are so small that the light will not be seen. It won't scatter it. It won't deflect it. Right? You won't see. But in the colloid, because the particles are a bit bigger, right, the light comes in here and it hits these particles different than some of the other ones. All of a sudden, that beam becomes visible, like your high beams of your car on a foggy morning. All right. Like in spy movies, right, when they're trying to go through like laser beam tripwires and they spray that fog or smog or smoke or whatever it is, and all of a sudden you see the beam, they have made the air in that area become a colloid by polluting it. So if we look at something and it is cloudy naturally, it will scatter light, meaning you'll see the beam, it's a colloid. If it's clear, it's a solution. It won't scatter light. Right, so same story, two paths. Yes, I see the beam, it scatters light, it's a colloid. No, I don't see the beam, it does not scatter light, it's a solution. Right, so this is how we tell the difference between those two. So you ask yourself, is it a suspension first? Then you move on, and then you ask about, is it scattering light? And that's how you can tell what each of these are. So if I brought up a picture like this one, And I wanted you to say, what are each of these substances, which look pretty darn similar to each other, right? I would go through the following process for each of these unknown ones. I'd say letter A, does it separate while standing? It does not. I see one uniform substance there, so I know it's not a suspension. Then you can see we're shining light beam through all of it. So then I move on to, does it scatter light? It does not. Letter A is a solution. Right? I look into B. Is it separating into layers while standing? It is not, so it's not a suspension. I look in, do I see a light beam? I do not, right? I see some flickers there, but I think that's probably just off the glass, right? Not a solid line like these guys, right? That means this is a solution. So all of the ones that meet those criteria are going to be solutions. So A and B, letter D, letter G, letter J are all not separating while standing, and they don't scatter light, so they're all solutions. Right? Letter C, maybe letter E, little beam there. Letter F for sure, maybe letter H, little beam there. Letter I for sure, letter L for sure, maybe K. It just depends on how much you see the beam. All right, so these guys here, C, F, I, and L, are clear-cut colloids. They don't separate while standing, but they do scatter light, so you see the laser beam going through. These ones here, I'd probably isolate those more, all right, and look at them individually to make sure it's not like reflecting light off the beam next to it, right? Notice these ones are kind of flicking when they sit next door to one who is a colloid. So my most likely scenario is that it's bouncing light back off of it, and that's what we're seeing up in here, the reflection of the colloid, but we'd have to do them individually to be sure. All right, so that's how you tell if it's a suspension, a solution, or a colloid. So let's look at some more of the everyday variety, right, if we wanted to identify these. All right, so I bring up this beaker here. I've got a sandy water, right, beaker. It's got oil in it to boot. So we've got 3 different things in it. It's a mixture. Right? There's oil, there's water, and there's sand. Each one of those things is a separate compound, which means by definition, it's a mixture. What type of mixture? I look at the thing. Does it separate while standing? Can it be filtered? Yes, it can. You may stop. You know it is a suspension. Right? Let's look at it something like this. Right? I see a mixture here, and it's going to be worthwhile to talk about what do we have mixtures of, right? So up here, we have 3 compounds, but we also had a liquid, solid, liquid mixture. So we had liquids and solids mixing. Here, we've got like gas, right? The air there is a gas, right? And we've got smoke. And remember, smoke is just like solid particulate matter in there. So we're looking at a solid gas mixture in here. So does it separate while standing? All right. No, right? That smoke looks pretty uniform, right? It doesn't pull into pieces. Then I ask myself, is it clear or is it cloudy? All right. Because the smoke is cloudy, it would scatter light. We know it to be a colloid. Right? So you kind of want to ask yourself, what phase are you looking at? And then does it separate, followed by clear or cloudy? All right. So we look at this guy, which is a glass of Sprite. Does it separate while standing? Right? It's a liquid. Solid mixture because there's sugar dissolved in there that we don't see. There's actually a gas in there as well that we don't see, right? Carbon dioxide, carbonation. All right, so we've got liquids, gases, and some dissolved solid in there. All right. Does it separate while standing? It does not. So we know it's not a suspension. We look at it. Is it clear or cloudy? It's clear, so it's a solution. All right, look at this thing down here. We've got whipped cream. Right? What's whipped cream a mixture of? A couple things. It's got sugar in it. Right? It's got some water in it. Right? It's got some gas in it, which makes it foamy. Right? So we've got liquids and gases in there. So we can usually attack it the same way. Does it separate while standing? Nope. Not a suspension. Is it clear or is it cloudy? It is cloudy. All right. So it would be a colloid. All right, we go up to here. All right. Here's a glass that has some fat in it. All right, so we have a liquid mixture. I look at it. Does it separate while standing? It sure does. I can stop. I know it's a suspension. Looking at this one here, right? This is mayonnaise. All right, mayonnaise has a couple different things in it, right? It's got some milk, but clearly it's got liquid particles in there. Right? And as long as it has a liquid or a gas, you can use this system, right, to attack it. All right, so we look, does it separate while standing? It does not. Is it clear? Is it cloudy? It is cloudy, which means it's a colloid. All right, look at this guy here, glass of beer. Right, we look at the liquid. Beer's got a bunch of things in it, right? It's got carbonation, right? So it's got carbon dioxide. Fundamentally, it's mostly water. Okay, it's got obviously ethanol, ethyl alcohol in it. All right, it's got hops. It's got all sorts of dissolved grains, all sorts of different things. All right, mixed in beer. All right, but fundamentally, they call it another fancy word. They call it the dispersing medium, right? The main component is liquid. So we can say, does it separate while standing? It does not. Is it clear? Is it cloudy? It is clear. I can see through it. It has color, but it's clear. I can see through it. Therefore, it is a solution. Now, the foam above it is a different story. The foam would be more like the whipped cream, right? The foam that you see at the above is changed state. It's a new substance. That's why it's on top. That foam up there, that foam doesn't separate while standing. But it is not clear, so the foam would be a colloid, which is similar characteristic of all foams. Then last but not least, here's starchy water, like potato starch, which would be one of the ways you could kind of start making gravy. You look at the thing, what's in there, right? It's a solid dissolved in a liquid, so it's got liquid in it. We look at it. Does it separate while standing? It doesn't. I'm not seeing layers, so it's not a suspension. Is it clear? Is it cloudy? It is cloudy. Therefore, it would be a colloid. All right, so that's how you want to go through and check your substances. Does it separate while standing, or can I filter it? It's a suspension. If the answer to that is no, is it clear? Solution. Is it cloudy? Then it is a colloid. All right, so what do we do then if our mixture doesn't have liquid or gas in it? Because that system works so long as our dispersing medium is a liquid or a gas. What if we have a solid mixture? Well, the first thing I can say is, it can't be a suspension if I have a solid, because it can't possibly separate while standing, right? If I pick the solid up, it all sticks together. So it can't pull apart into layers. So now you're just down to a 50-50. Is it a solution or is it a colloid? Right? And we go back to the whole homogeneous, heterogeneous thing. Solutions are homogeneous, so they look like one thing. Colloids are heterogeneous, so I fundamentally would see the pieces. You can't say, is it clear or is it cloudy, because you can't see through it, right? If I shine light on it, it's not even going to enter it because the particles. So what you do is you say, does it look like one thing, or do I see the pieces? So if I bring up an example of a solid mixture like brass, which is a mixture of zinc and copper, I look at that thing. It doesn't have liquid or gas in it, so I can't use my normal system. So I simply ask myself, does it look like one thing, or do I see the pieces? And the brass looks like one thing. So because it looks like one thing, it is a solution. And that is all alloys. Right? All alloys tend to be, or most alloys tend to be solutions because they look uniform. On the other hand, if I look at some solid mixtures like stained glass or gemstones, things like this, if I look at those, I can see the pieces. If you think of a pearl, you think of that like foggy white look that it has. If you look at all these gemstones, you see some of that like milky white looking substance inside the colors of the gemstones. And because we see the differences there, that means it is not uniform. Gemstones would be a great example of colloids. All right, so that's it for solution suspensions and colloids. That should give you guys everything you need to solve page 400, numbers 1 through 5. Tomorrow, we'll kick off with a recap of the solutions, the suspensions, and the colloids. We'll try to identify some more everyday ones just to make sure you guys have it. And then we'll jump into electrolytes and solution equilibrium just to get some topics out of the way. And we'll be at our regular 1 o'clock meet time tomorrow. Right? No meet today. Just make sure you guys watch the video here. And I will attach the PowerPoint that I was teaching off of in the parent square. I hope everybody's doing good. Look forward to seeing you guys soon.